Hello gang. Today we're going to discuss the last chapter in this Cisco model, chapter 11, and it's on network address translation in IPv4. So we're going to talk about network address translation, which is commonly called NAT. We'll talk about how NAT operates. We'll talk about configuring and troubleshooting NAT, and then we'll have a brief summary. So we're going to look at some of the characteristics of NAT. We'll describe the benefits and drawbacks. We'll discuss how to set up NAT with the CLI in both static and dynamic settings. We'll also talk about dynamic NAT. We'll talk about PAT as well, which is a port address translation. It's a lot like NAT, but you'll see there's a few differences. Then we'll talk about port forwarding using the CLI. And if you're going to enable NAT, port forwarding is something that you're probably going to end up needing to do. And then we'll also talk about NAT 64. Okay, so the reason that NAT exists is because if you think about IP4, it's not big enough for everything that is now connected to the internet. Most of us have more than one IP address in use at home at any one time, and some of us even have 10 or 11 because, maybe you've got a laptop and some people that live with you have laptops, and then you've got a phone and they've got a phone, and you've got an iPad or another tablet. Then on top of that, lots of other devices are connected now. If you've got a PlayStation or a Wii U or even some cable boxes, DirecTV, Dish, all of those things need an IP address. And because so many things are on the internet now, there just aren't enough IP4 addresses to handle this. So the idea of NAT was to help with that problem by using private address spaces internally. And network private addresses are described in Internet's RFC 1918. There are a set for each class. There's an A, a B, and a C in the private range. The private addresses are not routed by Internet routers. By default, they're set up where they're not routed out on the Internet. This private space helps some with the problem of running out of IP4 addresses. Now, it's important to take note here while we're talking about IP4. IP6 was designed to alleviate this problem and for the need of NAT to actually go away. But with IP4 still running so many things and so many places using it, the whole idea of NAT was to kind of come in there and help alleviate the problem. And on top of that, it does add some security because since those local addresses are not routed, you have a little bit more security in your network because everything is private. So here is a little graphic that actually just shows the private ranges in an A, B, and a C network. Class A, anything that's 10 dot is a private range, and that is the /8. With Class B's, it's anything from 172.16.0.0 to 172.31.255.255. And then finally, Class C is anything that's 192.168. By default, most of you probably are using a 192.168 something address. Very common for lots of home routers to have 192.168. 1.1 is the gateway, and then 1. Whatever be an address on the actual network. And they've also got a graphic down here showing that a NAT router translates those addresses from public to private when they need to actually go out on the internet. So NAT is the process that is used to actually translate network addresses. NAT's primary use is to conserve public IP4 addresses. NAT is usually implemented at a border network device such as a firewall or a router. It allows the networks to use private addresses internally, only translating when public IP access is needed. Devices within the organization can be assigned private addresses and operate with local unique addresses. Finally, when traffic needs to be sent or received outside or on the internet, the border router will perform NAT to actually get a public address to send the information out on the network. A good example of this is the network at BIPSI. BIPSI uses internal addresses, and they assign subnets to each, pretty much each lab. And then those classes, that's for each building's got a different set. So internally, you can route anything between the buildings that's needed. But until you actually go out to, say, www.cnn.com or something like that, you don't get access to a public IP because you don't need it. When you finally need a public IP, you'll send a request, and that'll go to their border gateway that will actually send it out to get the information off the internet. So here they're just giving a little example of that. We've got a 10.1.1.0 network serial connection between a couple of routers. And internally, we've got a 192.168.10 and a 192.168.11. You'll notice that /24 tells us those are two different class Cs that are connected. Router 2 is actually connected out onto the internet, though. So router 2 is where NAT would be turned on. So when a machine inside needs to connect out, it would go through router 2 that would perform the NAT to actually send the data out. So there's some terminology to be aware of in dealing with NAT. The inside network is basically either the LAN or the WAN that's internal that's using the private addresses. Outside refers to everything else. NAT includes 4 types of addresses: inside local and inside global, then outside local and outside global. And we'll talk about each of those. Here we've just got another example showing the inside network and the outside network. It's important to note that you see the picture of the cloud on both sides. The internal network can be quite large before NAT translation has to actually take place. There are several factors on it, and larger companies may not use one single external IP address. They may have an entire class of addresses or a set of 10 or 20 that they're going to use on rotation for different things. So static NAT uses a one-to-one mapping of local and global addresses. These are configured by your admin, and they remain constant. Static NAT is particularly useful when servers are hosted inside but must be accessed from outside. And their example, a network admin can SSH into a server inside the network by pointing the SSH clients to the proper inside global address. So here we have an example of that. And in their example, a static from 192.168.10.10 is set up with 209.165.200.226. So static is useful, but it really doesn't conserve a lot of addresses because there's that one-to-one mapping. Dynamic, on the other hand, uses a pool of public addresses and assigns them on a first-come, first-served basis. When an inside device needs access to an outside network, Dynamic will assign an available IP4 address out of the pool. Dynamic requires enough public addresses available to satisfy the total number of simultaneous connections. So here's an example of Dynamic, and you see that they're just assigned as they're needed. Port address translation, or PAT, maps multiple private IP4 addresses to a single public IP4 or just a few addresses. PAT uses the pair source port and source IP to keep track of what is going on. PAT is also sometimes called NAT overload. And I'll tell you, to be honest, it's important you understand the difference in these. But in the real world, when people talk about this, they pretty much call PAT and NAT the same thing. They call all of it NAT, even though a lot of what they're doing is actually a port translation. By also using the port number, PAT forwards the response packets to the correct internal device. So that's how you can set it up so that the outside can get to the inside. The PAT process can also validate those packets, adding a degree of security. So here's just a great little example where we're going to compare NAT and PAT. NAT translates IP4s on a one-to-one between private and public. PAT modifies both the address and the port number. NAT forwards incoming packets to their destination provided by the host on a public network. With PAT, there is generally only one or very few publicly exposed IP addresses. PAT is able to translate protocols that do not use port numbers, such as ICMP, which remember is ping. Each of these protocols is supported differently by PAT. So some of the benefits of NAT is that we are conserving the legally registered IP addresses. As a business, if you're going to get IPs from your ISP, you're going to pay for them. So the less you can use, the more you're going to save on money. We're providing some extra security. It really increases the flexibility of connections to the public network, and it provides a consistency for the internal networking addresses because you can set them up however you want and you can maintain consistency. I've seen lots of places that are rather large, like BIPSI and other colleges, use the 10 dot scheme because there are so many available in Class A, and they will assign each building a B inside of that A, like 10.1, 10.2, 10.3. Then you can go on and assign each floor one of those, 10.1.1, 10.1.2, or each lab or whatever, so that you can break it down, and then you can kind of look at an address and say, oh, all right, 10.1, I immediately know that that's the, this building, and then the .3 tells me it's the third floor in that building. So there are some disadvantages. There is a performance degradation, and there's really no way around it because it takes processing power to actually perform NAT. End-to-end functionality is degraded because direct connections are not available unless they're set up. End-to-end IP traceability is lost. Tunneling does become more complicated because now we've got to tunnel through an external into an internal network. And initiating TCP connections can be disrupted. So now we're going to talk about how to actually configure NAT. There are two basic tasks to perform when we're going to do static NAT. We need to create the mapping and then define the interfaces that belong to the inside and those that belong to the outside. So here we've just got a little example. They're showing how to set it up. We've got a router, we've got an internal and an outside network. First thing we're going to do is IPNAT inside source static, and then we're going to assign those addresses. We're showing first our internal address, which in this case is a 192.168.10.254, and it's followed by our external address. In this case, 209.165.201.5. Once we've issued that command, we've got to go to our other interfaces, assign them addresses, and then the IPNAT inside command or an IPNAT outside command will say what address is set to which. So here now we've got a static NAT set up between those two. And notice in our little table we're seeing we have an inside address and an outside address. To verify that NAT is running, we can do a show IPNet translations command. And that will basically print from the CLI the table that we were talking about earlier. Notice it looks a little different when there's actually an active session going on. If we do a show IP NAT translation and nothing's going on, it shows it's set up, but there's no outside local or global. If we do it while a connection is actually taking place, it'll show that it's there. Here to go on and verify, you can do a clear your stats and then re-show them. And hits and misses will go up or down based on how many packets are actually being sent over. So dynamic, remember, uses a pool of addresses and is sort of a first come, first serve. It is available, as long as you have enough IPs for it, this is a good way to go. The pool, again, though, has to be large enough to accommodate all of the inside devices. If the pool runs out, the devices just aren't able to communicate. So setting up dynamic NAT is sort of a 5-step process. First, you've got to define your pool with the IP NAT pool command. Give it a name, it'll make it easier. Then you've got to configure a standard access list permitting the addresses that should be translated. Remember your ACLs from last time. You've got to create an ACL and permit to allow those to happen. They put it on here in italics. I think it's important to remember you've got to use wildcards instead of subnet masks when you're dealing with ACL lists. Step 3 is to establish the dynamic source translation, and that's done by IPNAT inside source list, then your access list number. I believe you can do a name there, and then pool in the name. Finally, identify the inside with the interface and then IPNAT inside. Then do an IF command on your IPNAT outside as well to define the two addresses. So here is just an example of that, of dynamic NAT. You see we've got 2 internal with a router, then a border router, router 2, connecting to the internet with external addresses. Using the commands from before, that would set up and allow the table at the bottom with the inside and the outside addresses. And here we're just looking at the same thing. So you can verify dynamic very much like you can verify static with a show IPNAT translation command. Notice the top will show that they're not in use because the outside local and outside global are empty. Show IPNAT translations verbose will also give that information, and it'll give a little bit extra because it'll go on to say that you've got packets going and how much time is left. Clear IPNet stats will also clear everything so that you can do it again and look to actually see how many packets at that moment are going in and out the interface. So with PAT, it's a little different. With PAT, you've got to set up your pool. Here they're doing the pool, then the net mask, your access list, then IPNAT inside source list 1 pool, in this case NAT pool 2 overload. So to do PAT, you actually issue the NAT command with the word overload. And then again assign an outside and an inside interface. So with a single address with PAT, you're going to find a standard access list. You're going to set up the dynamic source translation with the ACL, which we talked about. Then identify the inside and the outside. So here we've got an example of PAT showing from PCs to servers. Just an example of what ports are open. In this case, they're the same. The interesting thing to remember is the ports don't have to be the same internal and external. For example, I could open port 80 on the outside for a web interface, but inside I could have that mapped to a server using port 8080 or 1080, anything I wanted to really. I could also open port 81 on the outside and have that go to port 80 on a different server on the inside. So that's how you're able to run multiple services on a single server like that, or a single outside address. So here to verify PAT, we can do a show IPNAT translation. And you see here that inside and outside global and local this time have ports next to them to show that port translations are happening. Port forwarding is something that's used a lot, and I just touched on it, but it's the act of forwarding a network port from one node to another. A packet is sent to the public IP port on a router, and it's forwarded to a private IP address and port inside the network. This is very helpful where servers have private addresses not reachable from the outside, but the server needs to be reached from the outside for some reason. So here they've got an example showing a small home office, and in this case we're forwarding port 80. And they're doing it graphically, but if you look, we're forwarding outside port 80 to an inside, then tell it what protocol you're going to allow, and voila, you're good to go. In iOS, the way that you forward a port, it's essentially a static NAT translation with a specified TCP or UDP port number. So in this case, we're going to use our same command, IPNAT inside source static, then we're going to say TCP or UDP, IP address space port, space external IP address, space port. Then again, if we haven't done it, we have to say what interface is NAT inside and what interface is NAT outside. Okay, so a question that gets asked is, what about NAT for IPv6? Well, remember that NAT was designed to help with IP4 address scarcity. IP6s have 128-bit addresses instead of what we use in IP4. And that provides 340, I don't even know how to say that, undecillion addresses. I can tell you that from something I read, this is the best way to understand how many IP6 addresses there truly are. In one of the FreeBSD books, they say that IP6 has enough addresses to assign every atom that makes up the Earth an IP address. And there will still be enough IP addresses left over to assign 10 more Earths IP addresses. The truth is that we should not in our lifetimes, once we're moved to IP6, run out of addresses. They may eventually, but it should be way, way, way beyond anything we have to worry about. So IP6, basically the point of that is that address space is not an issue. IP6 makes IP4 public-private NAT unnecessary by design. However, it does implement a form of a private address, but it's implemented differently than it is for IP4. And in IP6, that is the unique local address. And this is designed to allow IP6 communication within a local site. ULAs are not meant to provide additional IP6 space. They always have the prefix FC00, which results in the range FC00 to FDFF. ULAs are known as local IP6 addresses. Now that is not the same thing as a linked local address. That's important. So from that, IP6 uses NAT in a way, but in a much different context. In IP6, NAT is used to provide transparent communication between 6 and 4. NAT64 is not intended to be a permanent solution, but it's meant to be a transition mechanism. Network address translation or protocol translation is another NAT translation or transition mechanism for 6, but has now been depreciated. NAT64 is what is now recommended. And here we've got an example. So what we're doing with NAT64 is we're using an internal IP6 only, but externally we need that to go to IP4 and IP6 networks. So our NAT64 translation actually will take internally IP6 addresses and translate those to IP4 to be sent out on the internet. It'll get the data back, retransmit it into a 6 packet, and send it back out on the local network. So there's some things you can do if you need to troubleshoot NAT as well. One of the first things is to look and see what you've got. So you can clear the statistics, and then you can actually clear the translations. Then do a show statistics to see what's going on, and do a show translations to see that it's actually set up. The IP debug command, or debug IP NAT, will actually show a line by line of what data is coming in on what port and going out on what port. This is good to see that it's actually working, but this is going to create a lot of traffic, a lot of data. So you're not going to want to leave this on very long. And that is a rundown of NAT. Again, NAT summary, the NAT was used to alleviate the depletion of IP4 addresses. It conserves public address space, and it's truly the reason that we haven't been in a huge hurry to go completely over to IP6. I mean, we are out of IP4 addresses, but most of us at home with cable or DSL or whatever we may have tons of devices, but we only need one actual external device, our external IP address, to make that work. So we also discussed that NAT and PAT, NAT overloading and dynamic and static NAT, are all a little bit different, but they're all configured very similarly. We also talked about port forwarding and how to use the NAT show and debug commands. And finally, we discussed that IP6 uses something like NAT with NAT64, but it has a different purpose because there is no reason to conserve IP6 addresses. There are so many of them. Thanks for watching, everyone. This concludes the section of the second Cisco module. Have a good day.